All right, so this is another important article that I'm going to be explaining this paper, domain generalization via imprecise learning. And he's a very good researcher. So we need a little bit background. You're familiar with empirical risk minimization, this one. Just because we don't know the true probability distribution, we always approximate it. And as the VC dimension, which is a measure of the complexity of your model, increases, the gap between empirical risk and the guaranteed risk, or even the regularizers, increases. But there is an upper bound. The probability that test error is less than training error plus this value is 1 minus eta. And D here is just the VC dimension. N is the size of training set. Of course, if you increase the training set, then you have a better model, because deep learning is very data hungry. That's why we use all kinds of data augmentation in all paradigms. For example, in contrastive learning, we use different kinds of data augmentation. But deep learning is data hungry. You always need to feed it. That's why people invented other paradigms like zero-shot learning, few-shot learning. But still, all of them are doing the traditional learning, so still suffers from because the complexity, when complexity increases, then you need to give it more training samples. So out of distribution generalization is challenging because it involves not only learning from empirical data, but also deciding among various notions of generalization. For example, optimizing the average case risk, worst case risk, or interpolation. While this choice should in principle be made by the model operator like medical doctors, this information might not always be available in training time. The institutional separation between machine learners and model operators leads to arbitrary commitments to specific generalization strategies by machine learners due to these deployment uncertainties. We introduced the imprecise domain generalization framework to mitigate this, featuring an imprecise risk optimization that allows learners to stay imprecise by optimizing against a continuous spectrum of generalization strategies during training, and a model framework that allows operators to specify their generalization preference deployment. So in machine learning, traditionally we use IID, which is a wrong assumption. Of course, our modeling is very naive. For example, all kinds of message passing you see in graph neural network. They don't care about topological thing and geometric thing of the graph. That's why they need k layers just for k hop. And even if they use k layers, still they cannot classify a molecule or well. So that's why our modeling is wrong. Our modeling is wrong, and our solution is unfortunately things like domain adaptation, domain generalization, which I don't think your brain does like that. Your brain at the modeling stage, your model is good for generalization. We don't fix it with domain adaptation or model editing or different paradigms that we see today, everyday new paradigm, just because we don't go to the fundamental and see why we don't have a good generalization, because we don't care about topological deep learning, we don't care about geometric deep learning, and these topics that are relatively new to people. But what is precise generalization? Precision generalization hinges on the assumption that the learner's objectives align with the operator's goal, necessitating close collaboration during model development. However, this approach presents two primary drawbacks. Firstly, institutional separation between the machine learning engineers and the model operators, for example, the doctors, can make collaboration costly. Secondly, tailoring the model to a specific operator may restrict its deployment usability, as the operator's beliefs can change or conflicts may emerge when the model is operated by a different individual. You see an illustration of proposed imprecise learning framework that we allow learners to stay imprecise to avoid overcommit in light of generalization uncertainty. Instead, we defer this choice of precise generalization to the operator. Operator could be your doctor. For example, it says too conservative, or I choose my risk level. So we have a data and you have precise probability, which is, for example, your worst case. And we have a cradle set. So the engineer might anticipate the doctor's generalization strategy during the model training phase. So the concept IID assumption, as I said, this concept is formalized by finding the function f that minimizes the population risk for P, known as the Bayes optimal model. And then we use the empirical risk, and then we use a regularizer. So we advocate for an imprecise learning where learners do not commit to any particular P at training time, but express their uncertainty through this cradle set. So cradle set and partial preference, a crucial distinction between precise and imprecise learning lies in their approach to learners' preferences. Precise learners commit to specific distribution during training, creating a complete and transitive preference order based on empirical risk. That is, for any f and g, if f is greater than g, if and only if the risk is less than risk of g. The binary relation represented by k is such that if f is greater than g, then empirical risk of z is less than z of g. This leads to an incomplete preference ordering. So to facilitate learning, we need a certain notion of optimality taking into account k. We formalize this by considering an aggregated learning algorithm that takes a risk profile and returns a hypothesis. In particular, we focus on a specific type of aggregate function called an aggregate risk minimizers, where rho here is just a risk aggregation, which is indexed by lambda, which yields the non-negative real value statistical functional. It's a functional. What is a functional? You give it a function, returns a real value. We call lambda a choice space which arises exclusively due to imprecision of learning problem. So for each lambda, we denote the Bayes optimal model and the associated parameters. Now you need to know what is C Pareto optimality and C Pareto stationary and conditional value at risk. We use this in financial systems. It's a very good measure. Now they're using it in machine learning. So the algorithm is like this. Given the data from distinct domains: a loss function, a probability space, hypothesis space, a risk aggregator that we talked about, rho sub lambda, and the number of Monte Carlo samples. For example, we have m Monte Carlo samples. That's why we sum over m and we average them. Then we estimate Q star by solving 9, by computing this argmean of the gradient of risk with respect to rho. Then we compute v hat. Then we update our parameters. First we initialize it, now we update it until it is more than a threshold epsilon. So in our future work, we aim to broaden the scope of imprecise learning by implementing methods to elicit user preferences more effectively, improving computational efficiency. This approach would empower operators to weigh various criteria such as fairness, privacy, and algorithmic performance. You see, the directed acyclic graph of features and target CMNIST, that color and shape are affecting the Y. It could be red or green, and the shape could be different. So it is affecting the outcome. This is the data set that they have worked, and the measure is regret.